These are the answers to the AP Chemistry packet that covers topics 8.1 to 8.3. On this slide, you can see Unit 8 at a glance. Unit 8 is entitled Acids and Bases. In this video, we will take a look at topic 8.1, Introduction to Acids and Bases, topic 8.2, pH and pOH of strong acids and bases, and topic 8.3, weak acid and base equilibria. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 8.1, Introduction to Acids and Bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. The concentrations of hydronium ion and hydroxide ion are often reported as pH and pOH, respectively. And here are two equations that are listed on the AP Chemistry equations and constant sheet. The first one says pH is equal to the negative log of the concentration of the hydronium ion. And the second one says that pOH is equal to the negative log of the concentration of the hydroxide ion. The terms hydrogen ion and hydronium ion and the symbols H plus and H3O plus are often used interchangeably for the aqueous ion of hydrogen. Hydronium ion and H3O plus are preferred, but H plus is also accepted on the AP exam. Water autoionizes with an equilibrium constant Kw. Now, this equation is also featured on the AP Chemistry equations and constant sheet, and it says that Kw is equal to the product of the concentration of the hydronium ion times the concentration of the hydroxide ion. And at 25 degrees Celsius, Kw has a value of 1 times 10 to the negative 14. In pure water, pH equals pOH. Pure water is called a neutral solution. At 25 degrees Celsius, the value of the pKw is equal to 14, and thus pH equals pOH, which equals 7. The value of pKw is equal to 14, and that is equal to the sum of pH plus pOH at 25 degrees Celsius. And then finally, the value of Kw, the equilibrium constant for the autoionization of water, is temperature dependent. So the pH of pure, neutral water will deviate from 7.0 at temperatures other than 25 degrees Celsius. Now, before I get to question 1 in this packet, I would like to spend a moment reviewing a topic that you had learned about back in Unit 4. Unit 4 is entitled Chemical Reactions. This is topic 4.8, Introduction to Acid-Base Reactions. By definition, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Only in aqueous solutions, water plays an important role in many acid-base reactions, as its molecular structure allows it to accept protons from and donate protons to dissolved species. When an acid or base ionizes in water, the conjugate acid-base pairs can be identified and their relative strengths compared. Now, let's take a look at question 1. Actually, questions 1 and 2 in this packet were taken directly from the summative assessment practice for Unit 4. So at the top of this slide, it says, according to the Bronsted-Lowry definition of acids and bases, an acid is a substance that donates H plus ions, and a base is a substance that accepts H plus ions. Question 1, identify both sets of conjugate acid-base pairs in the reaction above. So on the left, we see a molecule HCN, that's hydrocyanic acid, and on the right, we see the Cn- or the cyanide ion. So since HCN lost H+, that makes it an H+ donor. So HCN behaves as an acid on the left, and its conjugate base is Cn- on the right. Water in this particular equation is behaving as a base. It is a proton acceptor, and when water accepts H+ from an acid, it forms the hydronium ion. The formula for the hydronium ion is H3O+. Here is question 2. Identify both sets of conjugate acid-base pairs in the reaction above. So the first chemical that I see is CH3NH2, which is called methylamine. Now on the right side of the equation, it has accepted H+, because now it's CH3NH3+, or the methylammonium ion. So the methylamine is actually behaving as a base, so that means that water is behaving as an acid. So water is a proton donor in this reaction. On the other side of the equation, we have the hydroxide ion. So when water loses H+, its conjugate base is the hydroxide ion OH-. So methylamine, CH3NH2, is behaving as a proton acceptor, a base, and the methylammonium ion, CH3NH3+, is its conjugate acid. In question 1, you observe that molecules of water can behave as proton acceptors, bases. In question 2, you observe that molecules of water can behave as proton donors, acids. The following particle diagram illustrates the process that occurs in pure water, known as the autoionization of water. In this reaction, we have two water molecules reacting with each other. One water molecule, acting as an acid, is a proton donor. Another water molecule, acting as a base, is a proton acceptor. And the products of this autoionization of water are the hydroxide ion, which is the conjugate base of water, and the hydronium ion, which is the conjugate acid of water. So in summary, one water molecule behaves as an acid, donating an H+ ion. Another water molecule behaves as a base, accepting an H+ ion, and the products are the conjugate base of water, which is the hydroxide ion, and the conjugate acid of water, which is the hydronium ion, H3O+. The chemical equation for the autoionization of water is shown below, along with the value of the equilibrium constant Kw at 25 degrees Celsius. An alternate form of the equation is also shown, in which the hydronium ion is replaced with the H+ ion. The letter P in symbols such as pH, POH, and pKw tells us to take the negative log of a quantity. The concentrations for ions such as H+ or OH- in aqueous solution have units of moles per liter, or molarity. Since the pH or POH is calculated from a logarithm function, the pH or POH does not have any units. Remember that hydronium, H3O+, and H+ can be used interchangeably. Now, on the bottom half of this slide, there are two equations listed. One of these equations is featured on the AP Chemistry equations and constant sheet, but the other one is not, and that's because you have to know how to reverse a logarithm. So the first equation that's listed, that is on the equation sheet, and it looks like this. If you know the value for the concentration of the hydronium ion, and you have to figure out the pH of the solution, the way you calculate the pH is you take the negative log of the concentration of the hydronium ion. But this other equation is simply the reversal of that process. And so this equation is not listed on the equation sheet. So if you already know the pH of the solution, then to calculate the concentration of the hydronium ion, then what you would do is you would take the number 10 and you would raise it to the negative pH power. And if you do that operation, then you get the concentration of the hydronium ion. There is a similar situation with POH. So take a look. This first equation is to calculate the POH. So if you know the value for the concentration of the hydroxide ion, to calculate the POH, you take the negative log of the concentration of the hydroxide ion. So that will give you the POH. the reverse, and this second equation is not listed on the equation sheet, is to take the number 10 and raise it to the negative POH power. And if you do that operation, then you will get the concentration of the hydroxide ion. And we'll see plenty of examples in this packet of how to do all these calculations. This equation, which is on the equation sheet, is talking about the kW. So at 25 degrees Celsius, the kW, which is the product of the concentration of hydronium times the concentration of hydroxide, has a value of 1.0 times 10 to the negative 14. And the negative log of that number is equal to 14. So the pKw, which is the negative log of the kW, is equal to the sum of pH plus POH. And that is equal to 14, but only at a temperature of 25 degrees Celsius. Now, here on this next slide, this is a portion of the AP Chemistry equations and constant sheet, and you can see that these equations that I'm highlighting on this slide can be found in the equilibrium section of the constants sheet. One more comment before we get to question 3 of the packet, and this is about significant figures. In this column on the far left, you see 3 different values for the concentration of the hydronium ion. 1 times 10 to the negative 3 moles per liter has only one significant digit. 1.2 times 10 to the negative 3 has 2 significant digits, and the number 1.22 times 10 to the negative 3 has 3 significant digits. When you take the negative log of those values, you will get a pH of either 3.0, 2.92, or 2.914. But what I'm doing is I'm rounding off to the proper number of significant digits. And with pH or POH, only the digits to the right of the decimal point are considered to be significant. So a pH of 3.0 has 1 significant digit. A pH of 2.92 has 2 significant digits, and a pH of 2.914 has 3 significant digits. This is question 3. It says, fill in the missing information in the tables below. The table on the left features concentration of hydronium ion and pH, and the table on the right features concentration of hydroxide ion, POH, as well as pH. Let's start with the table on the left. Remember that if you know the value of the concentration of the hydronium ion, then you can calculate the pH of the solution by taking the negative log of that concentration. So I'll start with 4.3 times 10 to the negative 5 moles per liter. That's the concentration of the hydronium ion. The negative log of that number is equal to 4.3665. Remember that only the digits to the right of the decimal are considered to be significant in a pH. So since 4.3 times 10 to the negative 5 has 2 significant digits, then I will round off my pH to 4.37 so that that value also has 2 significant digits. The next concentration of the hydronium ion that I see in the table on the left is 0.015 moles per liter. So that number has 2 significant digits. I take the negative log of that value, and I get 1.8239. Again, only focusing on the digits to the right of the decimal, I will round off the pH to a value of 1.82. Now, let's go in the other direction. If you know the pH of the solution, you can calculate the value for the concentration of the hydronium ion by doing 10 on your calculator raised to the negative whatever that pH value happens to be. So I see a pH of 11.65 in the table. So I will do 10 raised to the negative 11.65 on my calculator, and I get 2.2387 times 10 to the negative 12. Since 11.65 has 2 significant digits, then I will round off my concentration to 2 significant digits. That would be 2.2 times 10 to the negative 12 moles per liter. Now I see a pH of 6.14. So I'll pick up my calculator and I will put in 10 raised to the negative 6.14 power, and I get an answer of 7.2444 times 10 to the negative 7 moles per liter. Since 6.14 as a pH has 2 significant digits, I will round off my answer to 2 significant digits. That would be 7.2 times 10 to the negative 7 moles per liter. Now let's switch over to the table on the right. Remember that if you know the value for the concentration of hydroxide, then you calculate the pOH of the solution by taking the negative log of that concentration. So I see a concentration of hydroxide of 6.8 times 10 to the negative 6 moles per liter. I'll take the negative log of that number, and I get 5.1675. Since 6.8 times 10 to the negative 6 has 2 significant digits, then that means that the pOH should also have 2 significant digits. We only focus on the digits to the right of the decimal, so the pOH will be 5.17. Since all of these solutions are assumed to be at 25 degrees Celsius, then we can use the relationship which says that pH plus pOH equals 14. And since I already know the pOH is 5.17, that means that the pH would be 14 minus that value. So 14 minus 5.17 is 8.83. The next concentration of hydroxide that I see in the table is 2.8 times 10 to the negative 4 moles per liter. I'll take the negative log of that number, and I get 3.5528. I'm trying to get 2 significant digits in my pOH. That's going to be 3.55. And then the pH would be 14 minus 3.55, which equals 10.45. Now, we've gone from concentration of hydroxide to pOH. Let's go in the other direction. I see a pOH value of 10.39. So the concentration of hydroxide would be 10 raised to the minus 10.39. And so when I do that math, I get 4.0738 times 10 to the negative 11 moles per liter. Let me round that off to 2 significant figures because 10.39 has 2 significant figures. So that's going to be 4.1 times 10 to the negative 11 moles per liter for the concentration of hydroxide. The pH would be 14 minus the pOH, so 14 minus 10.39 is equal to 3.61. Now I see a pOH value of 8.04. That means that the concentration of hydroxide would equal 10 to the minus 8.04, and I get 9.1201 times 10 to the negative 9 moles per liter. Since 8.04 as a pOH value has 2 significant digits, I will round off my concentration of hydroxide to 2 significant digits. That would be 9.1 times 10 to the negative 9 moles per liter. And the pH would be 14 minus the pOH, so 14 minus 8.04 is equal to 5.96. So now this table is complete, and let's move on to question 4. Now, question 4 does not require any calculations, but we are looking at a trend in these two tables. So take a look at the concentration of the hydronium ion in the table on the left. Let's go from top to bottom in that table. Hopefully you can see that the concentration of the hydronium ion increases from top to bottom. Now, what happens to the pH values? They are decreasing. So as the value of the concentration of the hydronium ion increases, the value of pH decreases. In the table on the right, when we go from top to bottom, we see that the concentration of the hydroxide ion is increasing. Now, it does cause the value of pOH to decrease, but the question that we are asking ourselves in the second part of number 4 is, as the value of the concentration of hydroxide increases, what happens to the pH? So you can see that as pOH goes down, pH actually increases. So as the value for the concentration of hydroxide increases, the pH also increases. Now let's take a look at question 5 in your packet. It says, fill in the missing information in the table below. Assume that all solutions are at 25 degrees Celsius. So the columns in this table from left to right are the following. Concentration of H+, which is interchangeable with the hydronium ion. pH, concentration of hydroxide, pOH, and then finally a question about whether that solution in that row of the table should be classified as acidic or basic. So with respect to the calculations in question 5, hopefully at the end of question 5, you will appreciate how these quantities of H+ and OH-, their concentrations, and pH and pOH, they're all interconverted with the appropriate relationship mathematically. So as long as you know one of these 4 quantities, you can calculate the other 3. So let's get started with the first concentration that I see on the left, which is 0.075 moles per liter. So that is the concentration of H+. If I want to find the pH, I will take the negative log of that value. And so when I do the negative log of 0.075, I get 1.1249. All of the numbers in this table, as well as the ones in number 3 of the packet, they have 2 significant figures for the concentration, and the pH and pOH, because we only focus on the digits to the right of the decimal, they also have 2 significant figures. So everything in the table, calculation-wise, will be rounded to 2 significant figures for a concentration or 2 decimal places for a pH. So I'll say 1.12 for my pH. Now let's take a look at the relationship between the concentration of H+ and the concentration of OH-. So the product of those 2 multiplied together equals the Kw, which at 25 degrees Celsius is 1.0 times 10 to the negative 14. Since I already know the concentration of H+ is 0.075, what I have to do is take the Kw and divide by the concentration of H+. And so when I do that math, 1 times 10 to the negative 14 divided by 0.075, I get, when I round off to 2 significant figures, 1.3 times 10 to the negative 13 moles per liter. That is the concentration of the hydroxide ion. Now for the pOH, I could either take the negative log of the concentration of hydroxide, or I could realize that pH plus pOH equals 14 at 25 degrees Celsius. Since I already know the pH is 1.12, that means that the pOH is 14 minus 1.12, which is 12.88. Now, is this solution in this row of the table classified as acidic or basic? Let's compare the concentration of H+ with the concentration of OH-. If the concentration of H+ is greater, then the solution is acidic, which is what we see here in this example. Otherwise, if the concentration of hydroxide is greater, then the solution would be classified as basic. Now, the next row of the table, the number I see is 5.63, and that is the pH. So to go from the pH to the H+ concentration, I will do the reverse of the negative log, which means it will be 10 raised to the minus 5.63 power. And when I do that math, I get a concentration of 2.3 times 10 to the negative 6 when I round that answer off to 2 significant digits. Now, moving on to the concentration of hydroxide. Remember that the product of the concentration of H+ and OH- is equal to the Kw. Since I already know the concentration of H+, I will do 1 times 10 to the negative 14 divided by the concentration of H+, which is 2.3 times 10 to the negative 6, and I get that the concentration of hydroxide, when rounded off to 2 significant figures, is 4.3 times 10 to the negative 9 moles per liter. The pOH would be 14 minus the pH, so 14 minus 5.63 is 8.37. Now let's compare the concentrations of H+ and OH-. So it looks like the concentration of H+ in this solution is larger than the concentration of OH-, so therefore this would also be classified as an acidic solution. The next number in the next row of the table is the concentration of hydroxide, which is 3.8 times 10 to the negative 7 moles per liter. If I take the negative log of that number, I will get the pOH. So the negative log of 3.8 times 10 to the negative 7, when I round that off to 2 decimal places, it would be 6.42. So the pOH of 6.42 would be classified as 2 significant digits. Now, to move on to the next part of the row of the table, the pH is 14 minus the pOH. So 14 minus 6.42 is equal to 7.58. And now to get the concentration of H+, I will do 10 to the minus 7.58. And when I round that off to 2 significant digits, I get 2.6 times 10 to the negative 8 moles per liter. Now let's compare the concentration of H+ and OH-. So in this row of the table, it looks like the concentration of hydroxide is greater than the concentration of H+, so that solution would be classified as basic. Moving on to the final row of the table, I'll start with the pOH. So the concentration of hydroxide would be 10 raised to the minus 4.54. And when I round that concentration off to 2 significant digits, I get 2.9 times 10 to the negative 5 moles per liter. The pH would be 14 minus the pOH. So 14 minus 4.54 is 9.46. And the concentration of H+ would equal 10 raised to the minus 9.46 power. And when I round that answer off to 2 significant figures, I get 3.5 times 10 to the negative 10 moles per liter. Let's compare the concentration of H+ with the concentration of OH-. It looks like the concentration of hydroxide is greater than that of H+, so this solution is classified as basic. So hopefully at the end of question 5, you can now appreciate the relationship between H+, OH-, their concentrations, and pH and pOH, knowing that if you know one of these 4 quantities, you can calculate the other 3 based on the equations, which you can find on the AP Chemistry Equations and Constants sheet. Now, the instructions in question 5 said to assume that all solutions are at 25 degrees Celsius. One of the essential knowledge statements for topic 8.1 says that the value of Kw is temperature dependent. So the pH of pure, neutral water will deviate from 7.0 at temperatures other than 25 degrees Celsius. And that's what we're going to explore in question 6 of your packet. So at the top of this slide, I have the simplified version of the equation for the autoionization of water. It shows water on the left and the ions H+ and OH- on the right. The Kw for this reaction is equal to the product of the concentration of H+ times the concentration of OH-. And at 25 degrees Celsius, the value of Kw is 1.0 times 10 to the negative 14. The autoionization of water happens to be an endothermic reaction. And as you learned in Unit 7 on equilibrium, when you were studying Le Châtelier's principle, the value of the equilibrium constant is affected by changes in temperature. So in the table below, on the far left, you see that the temperature changes from 0 degrees Celsius to 50 degrees Celsius. The value of Kw is steadily increasing as you go from top to bottom down this table. So the Kw at 0 degrees Celsius is 1.14 times 10 to the negative 15. And the value of Kw at 50 degrees Celsius is a larger value. It's 5.48 times 10 to the negative 14. The next column in this table is the pKw. The pKw is simply the negative log of the Kw. So starting with that smallest value for Kw, 1.14 times 10 to the negative 15, when I take the negative log of that value, I get 14.943. And then when I go all the way up to the bottom part of the table, the largest value of Kw that is shown is 5.48 times 10 to the negative 14. When I take the negative log of that number, I get 13.261. Now, to give you some reference, this is all talking about pure water. This is not an acid. This is not a base. This is pure, neutral water. And pure water is always neutral at any temperature. And the reason why pure water is always neutral is because the concentration of H plus is equal to the concentration of OH minus. Therefore, pH equals POH. Now, to give you a reference point, let's focus on the temperature of 25 degrees Celsius. So we see that at 25 degrees Celsius, the approximate value for the kW is 1 times 10 to the negative 14. And the approximate value for the pKw at 25 degrees Celsius is 14. Since the pH is equal to the POH for pure, neutral water at any temperature, all I have to do to get the value of pH and POH is to divide the pKw by 2. In other words, cut that number in half. So what's half of 13.996 is 6.998. So what does this tell us? This tells us that pure, neutral water has a pH of approximately 7 at 25 degrees Celsius. But every single row of this table represents pure, neutral water. Now watch what happens as we lower the temperature of water from 25 degrees Celsius to 20 degrees Celsius. Now the pKw is 14.167, so half of that value is 7.084. When we go down to 10 degrees Celsius, the pKw of pure, neutral water is 14.533. We cut that number in half and we get 7.266. And at 0 degrees Celsius, the pKw of pure, neutral water is 14.943. We cut that number in half and we get 7.472. So we are not saying that at 0 degrees Celsius, water becomes basic. Water is neutral at any temperature. Pure water is always neutral at any temperature. Let's go higher than 25 degrees Celsius. So at 30 degrees Celsius, the pKw is 13.833. We cut that number in half and we get 6.916. At 40 degrees Celsius, the pKw is 13.535. We divide by 2 and we get 6.768. And at 50 degrees Celsius, we take 13.261, which is the pKw, divide that by 2, and we get 6.630. So we are not saying that when water is heated to a temperature above 25 degrees Celsius, it does not become acidic. It is still pure, neutral water at any temperature. So now that you've seen the answer to question 6 and how the kW, the pKw, the pH, and the POH vary with temperature, let's see if we can move on to question 7. You can answer these true-false statements. The first statement says, a sample of pure water has a pH of 7.0 at any temperature. So based on the answers to question 6, we know that that is not true. That when you go from a temperature of 0 degrees Celsius to a temperature of 50 degrees Celsius, we see wide variations in the pH of pure water. So the first statement is false. The next statement says that the concentration of H plus is equal to the concentration of OH minus in a sample of pure water at any temperature. That is definitely true. That is a good definition of why water is classified as neutral, because the concentration of H plus is equal to the concentration of OH minus. The next statement says a sample of pure water is neutral in which pH equals POH. Yes, that is also true. If the concentration of H plus is equal to the concentration of OH minus, then when you take the negative log of those values, you will get the same result. So pH equals POH is another good definition of what makes water neutral. The next statement says if the pH of the sample of pure water is less than 7, then the temperature of the sample must be less than 25 degrees Celsius. Let's take a look at the data from question 6. So where is the pH of pure water less than 7? It looks like it's at temperatures of 30, 40, and 50 degrees Celsius. And yet when the temperature is less than 25 degrees Celsius, the pH actually goes up, is higher than 7. So therefore that statement is false. If the pH of a sample of pure water is less than 7, then the temperature must be greater than, not less than, 25 degrees Celsius. All right, the next statement says, water ionizes to a greater extent at 50 degrees Celsius than it does at 25 degrees Celsius. So going from top to bottom down this table, we see that temperature increases. Also, going from top to bottom down this table, we see the value of kW increases. So the value of kW increases as the temperature increases. When you were studying Unit 7, Equilibrium, especially Le Châtelier's principle and the temperature dependence of the equilibrium constant, you observed that when you increase the temperature of a system, the equilibrium will shift in the direction of the endothermic process. So because the autoionization of water happens to be an endothermic reaction, that means that at a higher temperature, it's going to lead to a greater production of these aqueous ions. So that means that the ionization of water takes place to a greater extent at a higher temperature. So that is true. Water does ionize to a greater extent at 50 degrees Celsius than it does at 25 degrees Celsius. The next statement says, as the temperature increases, the pH of pure water decreases. And as we go from top to bottom down this table, we see that the temperature is increasing and the pH of pure water is decreasing. So yes, that is true. As the temperature increases, the pH of pure water decreases. And then our last statement, if a sample of pure water has a pH of 6.8, then the pOH of pure water must be 7.2. No, that's false. Pure water always has pH equal to pOH. Those values cannot be different from each other. They have to be equal. So pH equals pOH for pure, neutral water at any temperature. Now it's time to take a look at the next topic in this packet. This is topic 8.2, pH and pOH of strong acids and bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. Molecules of a strong acid, for example, HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HClO4, perchloric acid, H2SO4, sulfuric acid, and HNO3, nitric acid. These 6 strong acids will completely ionize in aqueous solution to produce hydronium ions and the conjugate base of the acid. The concentration of hydronium in a strong acid solution is equal to the initial concentration of the strong acid. The pH of the strong acid solution is easily calculated. When dissolved in solution, strong bases, for example, group 1 and group 2 hydroxides, completely dissociate to produce hydroxide ions. The concentration of hydroxide in a strong base solution is equal to the initial concentration of a group 1 hydroxide, or double the initial concentration of a group 2 hydroxide. The pOH and pH of the strong base solution is easily calculated. So from that first essential knowledge statement, here are the 6 strong acids that you should memorize for the AP Chemistry exam. Hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, perchloric acid, HClO4, nitric acid, HNO3, and sulfuric acid, H2SO4. A strong acid ionizes completely in aqueous solution to produce hydronium or H3O+ ions. Question 8. The following questions are related to strong acids. Assume that all solutions are at 25 degrees Celsius. Part A. What is the pH of 0.050 molar hydrochloric acid? So as you can see from the essential knowledge statement that I have highlighted on this slide, the concentration of the hydronium ion in a strong acid solution is equal to the initial concentration of the strong acid. So that's because a strong acid is 100% ionized in aqueous solution. So the pH of the strong acid solution is easily calculated. So the fact that HCl is a strong acid, then I know that the concentration of H plus is the same as the concentration of the acid itself. So all I have to do to get the pH is take the negative log of the concentration of the strong acid. So the pH is equal to the negative log of H plus, which in this example is equal to 0.050, and I get 1.3010 on my calculator. Now, since 0.050 has two significant digits, then I will round off my pH to 2 decimal places. So my answer to part A is 1.30. In part B, it's a similar situation. We have a different chemical, but it's also one of the 6 strong acids. This is HBr, and the concentration of the acid that we are given is the same as the concentration of the hydronium ion, or H+. So if I just take the negative log of this concentration, I will get the pH. The negative log of 2.5 times 10 to the negative 4, when rounded off to 2 decimal places, because 2.5 has 2 sig figs, I get 3.60 for my pH. Now, in part C, we're going to go in the opposite direction. It says, what is the concentration of a solution of perchloric acid, another example of one of the strong acids, and we are given that the pH is 4.25. So therefore, I'm going to go backwards by doing the inverse of the negative log, which means 10 raised to the minus 4.25 power. And when I do that math, I get 5.6234 times 10 to the negative 5. I will round this off to 2 significant figures because my pH has 2 decimal places. So 5.6 times 10 to the negative 5 moles per liter, that is the concentration of the strong acid, perchloric acid. And then part D, it's a similar calculation. We are given nitric acid, HNO3, which is another one of the strong acids. We're given the pH is 6.33. So 10 raised to the minus 6.33 power gives me, when rounded off to 2 significant figures, a concentration of 4.7 times 10 to the negative 7 moles per liter. That is the concentration of this strong acid, nitric acid. So you have seen the examples of the 6 strong acids that you need to memorize for the AP Chemistry exam. You've seen examples of calculations involving pH and concentration for strong acids. Now, let's take a look at examples of strong bases. The table above shows examples of group 1 and group 2 hydroxides. Sodium and potassium are located in group 1 on the periodic table, and calcium and strontium are located in group 2 on the periodic table. A strong base is an ionic solid that completely dissociates in aqueous solution to produce hydroxide ions. Notice that there's a little bit of a difference between the formula of these 4 compounds. With sodium hydroxide and potassium hydroxide, there is a 1-to-1 mole ratio between the formula of the compound itself and the moles of hydroxide ions that are produced in aqueous solution. But with the group 2 hydroxides, calcium hydroxide and strontium hydroxide, there is a 1-to-2 mole ratio between the formula of the compound itself and the number of moles of the hydroxide ions that are produced in aqueous solution. Now, on this next slide, you can see I'm highlighting some of the essential knowledge statements from topic 8.2 that are relevant to strong bases. The first one says that when dissolved in solution, strong bases For example, group 1 and group 2 hydroxides completely dissociate to produce hydroxide ions. But the next essential knowledge statement contrasts the difference between a group 1 and a group 2 hydroxide. So again, pay attention to that ratio. It says the concentration of hydroxide in a strong base solution is equal to the initial concentration of a group 1 hydroxide. That would be a 1-to-1 ratio for such compounds as sodium hydroxide or potassium hydroxide. But then it says is equal to double the initial concentration of a group 2 hydroxide. So that 2-to-1 ratio would be relevant for such compounds as calcium hydroxide or strontium or barium hydroxide. Finally, the pOH and pH of the strong base solution is easily calculated. Okay, now let's take a look at question 9 in the packet. With question 9, we have 4 bases: sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. Fill in the missing information in the table below. So in this table, we see the chemical formula of the base. We see the concentration of the base as well as the concentration of the hydroxide ion. Those two values are not necessarily going to be the same. We have the pOH and the pH. Let's start with sodium hydroxide. We are given that the concentration of sodium hydroxide is 0.15 moles per liter. Now, because when solid sodium hydroxide dissolves in water, there is a 1-to-1 mole ratio between NaOH and the hydroxide ion, then it is going to be the same as the concentration of the base. So the concentration of hydroxide is also 0.15 moles per liter. Now to get the pOH value, we take the negative log of the hydroxide concentration. So the negative log of 0.15 works out to be 0.8239. And since 0.15 has 2 significant digits, I will round off my pOH value to 0.82. Now to get to the pH from the pOH, remember that 14 equals the sum of pH plus pOH. We can assume that all temperatures are at 25 degrees Celsius unless otherwise told. So in this case, I can take 14 minus the pOH value to get the pH. So 14 minus 0.82 is equal to 13.18. Now that we've completed the first row of the table, the next row of the table involves a similar base. This is potassium hydroxide, but we have to go from pH all the way to concentration of base. So starting with pH, 11.51 is the pH. Since pH plus pOH is equal to 14, that means that the pOH will be 14 minus 11.51, and that works out to be 2.49. Now, to go from the pOH to the concentration of hydroxide, it will be the inverse of the negative log. So I'll do 10 raised to the minus 2.49 power. And when I do that math, I get 0.003236. And since 2.49 as a pOH value has 2 significant digits, only focusing on the digits to the right of the decimal, I will round off my concentration to 2 significant digits as well. So 0.0032 moles per liter is my concentration of hydroxide. Just like sodium hydroxide, potassium hydroxide has a 1-to-1 mole ratio between KOH and hydroxide. So the concentration of hydroxide is the same as the concentration of the entire base, KOH. So now that I've completed the second row of the table, I have to be careful with the next 2 rows of the table because now there is a 1-to-2 ratio between the formula of the compound and the number of moles of hydroxide. So I see calcium hydroxide has a concentration of 4.7 times 10 to the negative 5. Because of this 1-to-2 ratio between the formula of calcium hydroxide and the number of moles of hydroxide, I'm going to multiply the concentration of base times 2 to get the concentration of hydroxide itself. And when I do that, I get 9.4 times 10 to the negative 5 moles per liter. That is my concentration of hydroxide. Now I'm going to take the negative log of that value to get the pOH. So the negative log of 9.4 times 10 to the negative 5 is equal to 4.0269. And when I round that off to 2 decimal places based on the rules, having 2 sig figs in my concentration, that gives me a pOH of 4.03. The pH would be 14 minus that pOH value, so 14 minus 4.03 is 9.97. Now we're in the last row of the table. I'll start with the pH and I will eventually get to the concentration of barium hydroxide. So I'm given a pH. The pOH is 14 minus that value, so 14 minus 8.68 is 5.32. Now to get to the concentration of hydroxide in this solution, it's going to be the inverse of the negative log. So 10 raised to the minus 5.32 power, and then I round that off to 2 significant figures. Because 5.32 has 2 significant figures, I get 4.8 times 10 to the negative 6 moles per liter. Now this is the concentration of the hydroxide ion, but it's not the concentration of the barium hydroxide. I've already multiplied by 2 going from calcium hydroxide's concentration to the concentration of hydroxide itself. Now we're going to divide by 2. So because there is a 1:2 mole ratio between BaOH2 and hydroxide itself, I will divide by 2 to get the concentration of barium hydroxide. And so when I do that math, I get 2.4 times 10 to the negative 6 moles per liter. So that is the rest of the data. That's the answer to question 9. Now let's take a look at question 10 in the packet. Question 10 says, a student measures the pH of a 100.0 milliliter sample of aqueous sodium hydroxide and records the pH as 12.00. So you can see in the diagram that there is a beaker on the left that has a volume of 100.0 milliliters of aqueous sodium hydroxide, and the pH of that solution is equal to 12.00. Now the question goes on to say, calculate the volume of distilled water that should be added to this solution so that the pH of the diluted solution is equal to 11.00. So as we can see in the beaker on the right, we now have a new pH of 11.00, and we have a larger total volume of solution. So the strategy for solving this question is, let's go from pH to pOH, and then let's go from pOH to the concentration of hydroxide. And we'll do that for each beaker, the beaker on the left and the beaker on the right. So remember that 14 minus the pH is equal to the pOH. So if the pH is 12, then 14 minus 12 is 2. And if the pOH is 2, then the concentration of the hydroxide ion would be 1 times 10 to the minus 2. So in the original solution of 100.0 milliliters of aqueous sodium hydroxide, the concentration of the hydroxide ion is 1 times 10 to the negative 2. Now, watch what happens to the concentration of the hydroxide ion when this solution is diluted with water. So again, let's go from pH to pOH. So if the pH is 11, then 14 minus 11 is equal to 3. And if the pOH in that diluted solution is equal to 3, then the concentration of the hydroxide ion in that diluted solution is equal to 1 times 10 to the minus 3 moles per liter. So what happened to the pH upon dilution with water is the pH went down by 1 unit on the pH scale. But what happened to the concentration of the hydroxide ion is it decreased by a factor of 10. So to summarize, the student needs to dilute the sodium hydroxide solution by a factor of 10. So therefore, the volume needs to increase from 100 milliliters to 1,000 milliliters. So what volume of distilled water should be added to this solution? The answer is a total of 900 milliliters of distilled water should be added to the 100 milliliter sample of aqueous sodium hydroxide. All right, well, that is the answer to question 10. Now let's move on to the next question in this packet. This is question 11. It says a student combined 500 milliliters of 0.050 molar hydrochloric acid with 500 milliliters of 0.10 molar sodium hydroxide and mixed the final solution thoroughly. Part A, write the net ionic equation for the reaction that occurs when aqueous solutions of a strong acid and a strong base are combined. So in this example, the strong acid is hydrochloric acid, HCl. The strong base is sodium hydroxide, NaOH. We're definitely going to produce water when the H plus of hydrochloric acid combines with the OH minus of sodium hydroxide. And then we're also going to produce aqueous sodium chloride. So the products of this reaction are water, liquid water, and aqueous sodium chloride. Now, we still haven't written the net ionic equation for this reaction, but remember that a strong acid is 100% ionized in aqueous solution. So I'll break up hydrochloric acid into H plus and Cl minus. A strong base is completely dissociated into aqueous ions. So that would be Na plus and OH minus. So there's my strong acid and my strong base completely ionized and dissociated. And on the right side of the equation, water is a covalent molecular substance, so I'm not going to split that up. But sodium chloride is an aqueous ionic compound, and I would split that up into Na plus and Cl minus for an ionic compound in aqueous solution. Let me cross off my spectator ions on both sides. So I see chloride on the left, chloride on the right. I see sodium on the left and sodium on the right. And so what I have left is the H plus ion combining with the OH minus ion to produce water. And this is the net ionic equation for the reaction that occurs when aqueous solutions of any strong acid are combined with an aqueous solution of any strong base. All right, moving on to part B. Let's convert volume and molarity into moles. It says calculate the number of moles of HCl and the number of moles of sodium hydroxide, NaOH, that are present in the beginning of the experiment before the two solutions are combined. So volume times molarity equals moles. So 500 milliliters times 1 liter over 1,000 milliliters, that would be half a liter, multiplied by the molarity, which is 0.050 moles of HCl per liter. And if we do this math, we get 0.5 times 0.05, which is 0.025 moles of HCl. So that's present in the first beaker. Let's repeat that calculation using 500 milliliters of 0.10 molar sodium hydroxide. Again, we have half a liter, so 500 divided by 1,000, and then multiplied by the molarity, 0.10 moles of sodium hydroxide per liter. So 0.5 times 0.1 is equal to 0.050 moles of sodium hydroxide. Notice that these two quantities do not equal each other. So there is going to be an excess reactant as well as a limiting reactant in this reaction. Part C, calculate the number of moles of the excess reactant that remain left over in the combined solution. Assume that the acid-base reaction goes to completion. So HCl reacts with NaOH in a 1-to-1 mole ratio. It produces water and aqueous sodium chloride. But since these are not present in the two separate beakers in an equal amount of moles, the chemical that's going to be left over is the one that has a larger number of moles. So 0.025 is less than 0.050. There's going to be excess sodium hydroxide present in the combined solution at the end of the experiment. So 0.025 moles of HCl, in other words, all of it, reacts. HCl is the limiting reactant with 0.025 moles of sodium hydroxide to produce water and aqueous sodium chloride. So how much of the sodium hydroxide is left over at the end? It would be the amount present at the beginning, 0.05, minus the amount of sodium hydroxide that was consumed in the reaction. So the amount of excess sodium hydroxide left over is 0.05 minus 0.025. So in the combined solution at the end of the experiment, there is 0.025 moles of sodium hydroxide. Now, part D asks, calculate the pH of the combined solution at the end of the experiment. We know the amount of moles of sodium hydroxide, but we also know the volume is 1 liter. So the molarity of sodium hydroxide is also the concentration of hydroxide in that final beaker. The concentration of hydroxide is 0.025 moles per liter. To get the pH, first we're going to take the negative log of the hydroxide concentration to get the pOH, and then we'll do 14 minus the pOH to get the pH for our final answer. So the negative log of 0.025 will get us the pOH, and that works out to be 1.60 when I round that off to 2 decimal places because 0.025 has 2 significant digits. But 1.60 is not my final answer. They want the pH, and right now I have the pOH. So I still have to do 14 minus 1.60. And when I do that, I get 12.40. So the final answer for part D, the pH of the combined solution at the end of the experiment is 12.40. Now let's move on to question 12. I'd like to say something about questions 12 and 13 in this packet. Questions 12 and 13 are designed to be transitional questions. We're about to make a transition in this packet from topic 8.2 to topic 8.3. Topic 8.2 has to do with strong acids and bases. Topic 8.3 has to do with weak acids and bases. So as you're answering questions 12 and 13 in your packet, pay close attention to differences between a strong acid and a weak acid. All right, this is question 12. It says the table below contains information about 2 solutions with the same initial concentration of acid. So in the second column of this table, the initial concentration of the acid is 0.036 moles per liter. I'm going to teach you a formula for percent ionization. The formula for percent ionization is defined as follows. It is a ratio of the concentration of the hydronium ion in solution at equilibrium divided by the initial concentration of the acid itself, and then times 100. So for part A, use the formula above, the percent ionization formula, and the data in the table to calculate the percent ionization of the acid in a solution of 0.036 molar HNO3. Well, 0.036 divided by itself is 1. So therefore, for HNO3, it is 100% ionized. You probably recall that HNO3, which is known as nitric acid, is one of the 6 strong acids that you need to memorize for the AP Chemistry exam. So there's no surprise that nitric acid, HNO3, is 100% ionized in solution. It is, by definition, a strong acid. So what's happening with HNO2 is something different. Use the formula above for the percent ionization of the acid to calculate the percent ionization for 0.036 molar HNO2. HNO2 is not a strong acid. It's called nitrous acid, and you can tell it's a weak acid. Take a look. The concentration of the hydronium ion at equilibrium is 0.0036 moles per liter. So when you divide that value by the initial concentration of the acid, you get 10%. So that is a difference between a strong acid, such as HNO3, and a weak acid, such as HNO2. So part C says, based on your answer to part B, Explain why HNO2, nitrous acid, is classified as a weak acid. HNO2 is a weak acid because it is only partially ionized in aqueous solution, whereas HNO3, nitric acid, is a strong acid because it is 100% ionized in aqueous solution. There are only 6 strong acids that you have to memorize for the AP chemistry exam, but there's a vast list, plenty of examples of weak acids that we will talk about in topic 8.3. Now, before we take a look at question 13 in this packet, I'd like to show you these 2 particle diagrams. So the particle diagrams shown below should help you to compare the percent ionization for a strong acid, such as HNO3 or nitric acid, with the percent ionization for a weak acid, such as HNO2 or nitrous acid. As you can see near the top of this slide, there is a legend and a list of particles that may be present in these particle diagrams. And just below that legend is a comment indicating that water molecules are not shown in these particle diagrams. So I'm going to go ahead and list off the particles that may be present in these particle diagrams. So from left to right, these are the possible particles that may be present. We have HNO3 molecules, followed by NO3 minus ions, and then we have the hydronium ion, H3O plus, and then HNO2 molecules, and then finally NO2 minus ions. Now, let's focus our attention in the particle diagram on the left. I see a beaker, and it contains a 0.036 molar solution of HNO3, which is nitric acid. Now, nitric acid is on your list of 6 strong acids that you should memorize for the AP chemistry exam. The pH meter in that beaker indicates that the pH of that solution is 1.44. Now, when I look at the particles that are present, I do not see any HNO3 molecules at all. So why is that? Why are there no HNO3 molecules? Well, that's because this is a strong acid. So every single one of the HNO3 molecules has already lost H+. And when it lost H+, it was transferred to a water molecule. So what I can see are 10 hydronium ions and 10 nitrate ions. So that particle view shows me that every single one of those HNO3 molecules has already undergone the proton transfer, and that's 100% ionized. Now focus your attention in the beaker and the particle diagram on the right. So we have a 0.036 molar solution of HNO2 or nitrous acid, but HNO2 is not on your list of 6 strong acids. Notice that the pH meter does not say 1.44, but rather 2.44. So what that means is that the pH is higher, and it's actually higher by 1 unit on the pH scale. So every time you change by 1 unit on the pH scale, that is a 10-fold change in the concentration. So what we see is only 1 hydronium ion in that particle diagram on the right, where on the left we see 10 hydronium ions. So the concentration of hydronium is 1/10 as much in that beaker on the right. And when I count the particles, I can see 9 HNO2 molecules. I see 1 NO2 minus ion, and then 1 hydronium ion. So what that means is that only 1 out of 10 HNO2 molecules has undergone that proton transfer. So again, this is 10% ionization for a weak acid as compared to 100% ionization for a strong acid. Well, hopefully you can see in this compare and contrast that we have 100% ionization for a strong acid on the left, and we have only partial ionization for a weak acid on the right. All right, now let's go ahead and take a look at question 13 in the packet. Now we're still talking about nitric acid, HNO3, and nitrous acid, HNO2, but here's a different way of examining their properties. The table below contains information about two solutions with the same pH. So the pH is 1.86. Fill in the missing information in the table below. To go from the pH to the concentration of the hydronium ion, that would be 10 raised to the minus 1.86 power. And when you do that calculation, you get 0.01380, but I'll use two significant digits since a pH of 1.86 also has two significant digits. So I'm going to round that concentration of hydronium to 0.014. Now, for the percent ionization of the acid, we already know that nitric acid is on your list of 6 strong acids to memorize for the AP Chemistry exam. So by definition, nitric acid is 100% ionized. Therefore, the concentration, the initial concentration of the acid is 0.014 moles per liter. But what about the weak acid, HNO2? It's only partially ionized in solution. How do we figure out the percent ionization for HNO2 in this example? Remember that formula that I taught you, which, by the way, this formula is not on the equation sheet, so it's a good one for you to memorize. The percent ionization is the ratio of the hydronium ion concentration at equilibrium divided by the initial concentration of the acid itself. So 0.014 divided by 0.50 times 100, and that equals 2.8%. So HNO2 is a weak acid, only partially ionized in solution. Now that you've seen the answers to questions 12 and 13 in this packet, we are ready to make our transition to our last new topic in this packet. This is topic 8.3, weak acid and base equilibria. Here are the essential knowledge statements from the AP Chemistry course and exam description. Weak acids react with water to produce hydronium ions. However, only a small percentage of molecules of a weak acid will ionize in this way. Thus, the concentration of the hydronium ion is much less than the initial concentration of the molecular acid, and the vast majority of the acid molecules remain unionized. A solution of a weak acid involves equilibrium between an unionized acid and its conjugate base. The equilibrium constant for this reaction is Ka, often reported as pKa. The pH of a weak acid solution can be determined from the initial acid concentration and the pKa. So what you are seeing right now are two equations. These equations are listed on the AP Chemistry equations and constant sheet. The first one is the Ka expression. And you can see that in the numerator, it's the concentration of the hydronium ion times the concentration of A minus, and then divided by the concentration of HA. So in AP Chemistry, HA is the generic formula for a weak acid, and A minus is the generic formula for its conjugate base. You can also see the definition of pKa. pKa is equal to the negative log of Ka. Right, now let's talk about weak bases. Weak bases react with water to produce hydroxide ions in solution. However, ordinarily, just a small percentage of the molecules of a weak base in solution will ionize in this way. Thus, the concentration of the hydroxide ion in the solution does not equal the initial concentration of the base, and the vast majority of the base molecules remain unionized. A solution of a weak base involves equilibrium between an unionized base and its conjugate acid. The equilibrium constant for this reaction is Kb, often reported as pKb. The pH of a weak base solution can be determined from the initial base concentration and the pKb. Now, you can see two more equations. These equations are also listed on the AP Chemistry equation sheet. The first one is the Kb expression, and it's equal to the concentration of the hydroxide ion times the concentration of Hb plus, and then divided by the concentration of B. So in this representation, B represents the chemical formula of a substance that behaves as a weak base, and Hb plus represents the formula of its conjugate acid. And then also you can see pKb is defined as the negative log of Kb. All right, just a few more in topic 8.3. The percent ionization of a weak acid or base can be calculated from its pKa or pKb and the initial concentration of the acid or the base. The percent ionization can also be calculated from the initial concentration of the acid or the base and the equilibrium concentration of any of the species in the equilibrium expression. For any conjugate acid-base pair, the acid ionization constant, which is Ka, and the base ionization constant, which is Kb, are related by Kw. So these two equations also appear on the AP Chemistry equation sheet. The first one says that Kw, which is the autoionization constant for water, is equal to the product of Ka times Kb. And then that next equation says that the pKw is equal to the sum of pKa plus pKb. Now, here is a portion of the AP Chemistry equations and constant sheet, and you can see I have highlighted on this slide all of those equations that I mentioned for topic 8.3. They are featured on the AP Chemistry equation sheet. But notice on the right side of this slide, the equation for the percent ionization of a weak acid, which is equal to this ratio of concentration of the hydronium ion at equilibrium divided by the initial concentration of the weak acid times 100%, and then this corresponding equation for the percent ionization of a weak base. It's a similar ratio, but now because it's a base, it's the concentration of the hydroxide ion at equilibrium divided by the initial concentration of the weak base times 100. So I'm just showing you that these two equations do not appear on the equation sheet. So it's important that if you ever have to answer a question about the percent ionization of a weak acid or a weak base, these are equations that you should know because they are not listed on the AP Chemistry equation sheet. In this table, on the left, we see the 6 strong acids that you should memorize for the AP Chemistry exam: HCl, HBr, HI, HClO4, HNO3, and H2SO4. On the right, you see a list of examples of weak acids. A strong acid is 100% ionized in aqueous solution, whereas a weak acid is only partially ionized in aqueous solution. Note, partially ionized is not the same as partially soluble. A weak acid can be very soluble in water, but only a small fraction of the acid molecules are ionized in aqueous solution. So examples of weak acids include HF, C2H3O2, HNO2, etc. Question 14. Hydrofluoric acid, HF, is a weak acid that ionizes in aqueous solution according to the equation shown below. Part A. Write the expression for the equilibrium constant, Ka, for this reaction. Now, when you were learning about equilibrium in Unit 7, you learned that an equilibrium constant expression is written as products over reactants. You also learned that solids and pure liquids are not included in the equilibrium constant expression. So for this reaction between hydrofluoric acid HF and water to produce the fluoride ion F- and the hydronium ion, it's going to be liquid water that is not included in the Ka expression because pure liquids and solids are not included. So for this expression, products over reactants for Ka, it's going to be concentration of the fluoride ion F- times the concentration of the hydronium ion H3O+, and since water is not included in this expression, on the bottom will just be the concentration of hydrofluoric acid HF. Okay, now what I'd like to do is to compare the answer to part A of this question with the Ka expression that appears on the AP Chemistry equations and constant sheet. Take a look. Now hopefully you can see how similar these two Ka expressions are. So HF is the actual chemical formula of hydrofluoric acid, and F- or the fluoride ion is the chemical formula of the conjugate base of hydrofluoric acid. But in AP Chemistry, we use the generic chemical formula HA to represent any weak acid. And then A- is the generic chemical formula of the conjugate base of that weak acid. So side by side, you can see how similar these two expressions are. Now, there's one more thing I'd like to show you. And at the very bottom of this slide, what I've done is I've simplified the equation for the ionization of a weak acid HA. So what I'm showing is HA on the left and then H+ and A- on the right. So as you can see, H+ can be used in certain situations interchangeably with the hydronium ion H3O+. So if you ever see the expression that just shows HA or a weak acid splitting up into H+ and the conjugate base, then hopefully you can see how similar these two equations are. On the AP exam, the general preference is to show proton transfer to water to produce the hydronium ion. However, since H+ and H3O+ can be used interchangeably, I just wanted to make you aware of how those two equations are very similar to each other. All right, moving on to part B. The pH of 0.50 molar hydrofluoric acid is 1.74. Calculate the value of the concentration of H+ in 0.50 molar hydrofluoric acid. Since we are given the pH of this solution, and the pH is equal to the negative log of the concentration of H+, we're going to do the inverse of that procedure. So the inverse of a negative log is 10 raised to the minus pH. So the concentration of H+ is equal to 10 raised to the minus 1.74. And when we do that math, we get a concentration of H+ of 0.01820. Since the pH 1.74 has two significant digits, because we're only counting the digits to the right of the decimal, to round off our concentration to two significant digits gives us an answer of 0.018 moles per liter. Now that we know the concentration of H+ in this hydrofluoric acid solution, we can calculate the percent ionization. So the percent ionization will be a ratio of the concentration of H+ in equilibrium divided by the initial concentration of the molecular acid. So for this ratio, it's going to be 0.018, the concentration of H+, divided by the initial concentration of the molecular acid, 0.50. Then we take that ratio, multiply by 100, and we get 3.6% ionization for this acid. So the answer to part B is 0.018 moles per liter for the concentration of H+, and 3.6% ionization for the acid. Question 15. Acetic acid, HC2H3O2, is a weak acid found in household vinegar. Acetic acid ionizes in aqueous solution according to the equation shown below. Part A. Do you predict that the pH of 0.50 molar acetic acid should be less than, greater than, or equal to the pH of 0.50 molar hydrofluoric acid? Your justification should include a comparison of the Ka values for hydrofluoric acid and acetic acid, and a comparison of the relative strength of these two acids. So we are given in question 15 that the Ka for acetic acid is equal to 1.8 times 10 to the negative 5. And in question 14, we were given the Ka for hydrofluoric acid, which was 6.8 times 10 to the negative 4. Let's compare these two Ka values and take a look at which one is smaller and which one is larger. Since the Ka for acetic acid is smaller than the Ka for hydrofluoric acid, that means that this ionization reaction, the reaction of the acid with water to produce the hydronium ion, will take place to a smaller extent with acetic acid because it has a smaller Ka value. That makes acetic acid a weaker acid than hydrofluoric acid. The weaker the acid, the lesser the amount of ionization that will take place in aqueous solution. So we would expect the concentration of the hydronium ion to be smaller in the solution of acetic acid. What does a smaller amount of the hydronium ion do to affect the value of the pH? Well, the smaller the amount or the concentration of hydronium, the higher the pH will be. So our prediction is that acetic acid will have a higher pH than hydrofluoric acid. So here's the answer to part A. The pH of 0.50 molar acetic acid should be higher than or greater than the pH of 0.50 molar hydrofluoric acid. Acetic acid has a smaller Ka value than hydrofluoric acid does. This means that acetic acid is a weaker acid than hydrofluoric acid, and acetic acid should ionize to a lesser extent in aqueous solution. Since 0.50 molar acetic acid solution should contain fewer or a lower concentration of hydronium ions, it should have a higher pH value. Now remember that prediction that acetic acid has a higher pH value because we're going to see an answer in part D of question 15. So when we get to part D of question 15, we can check to see if our prediction in part A comes true. Let me go back and remind you, in question 14, the pH of 0.50 molar hydrofluoric acid was 1.74. So if our prediction that acetic acid will have a higher pH comes true, then the answer to part D should be higher than 1.74. So remember that number. All right, part B, we have a rice table that is incomplete. Fill in the missing information in the rice table below. Let the variable x represent the concentration of the hydronium ion at equilibrium. Now, before I start to fill in the missing information into this rice table, let me explain why we use a rice table to process the concentration of the hydronium ion at equilibrium for a weak acid. We know that the concentration of acetic acid is 0.50 molar. However, since acetic acid is not a strong acid, it is not 100% ionized in solution. So the concentration of the hydronium ion is not 0.50 molar. It's going to be some number that we don't know, but it's a relatively small amount since only part of the acetic acid will be ionized in aqueous solution. So for the reaction row of the rice table, we're talking about what happens when a weak acid reacts with water. This is the ionization of the weak acid. So on the left, we have the acetic acid, HC2H3O2. That's the formula of acetic acid. It reacts with water to produce the acetate ion, so C2H3O2 minus. That's called the acetate ion, which is the conjugate base of acetic acid. And it also produces the hydronium ion, H3O plus. So acetic acid is donating H plus to water. That's this particular reaction that we're looking at right now. Initially, we have a concentration of acetic acid, which is 0.50 molar, because we were given that value in this problem. We don't need to worry about the concentration of water. That's not something to consider at all, which is why I've written Na for not applicable for the concentration of water. And then initially, before this reaction takes place between acetic acid and water, the initial concentration of the acetate ion is 0. For the hydronium ion, I have written approximately 0, because technically in pure water, there is a little bit of the hydronium ion. In other words, in pure water, the pH is 7 at 25 degrees Celsius. So technically, the concentration of the hydronium ion is not 0, but it's 1 times 10 to the minus 7. So because it's a very, very small number, that's why I've written approximately 0. Now, as this reaction takes place between acetic acid and water, some of the acetic acid will be consumed. So it's going to be a change of minus X, because we don't know what that value is, at least not yet. As this reaction proceeds, the concentration of the acetate ion will increase. That'll be a change of plus X. And of course, because of the 1-to-1 ratio between the acetate ion and the hydronium ion on the right side of the equation, the change in the concentration of the hydronium ion will also be plus X. So as you look at the instructions for part B, it says let the variable X represent the concentration of the hydronium ion at equilibrium. In our final row of the rice table, the concentration of acetic acid at equilibrium would be 0.50 minus X. The concentration of the acetate ion at equilibrium will be X. And the concentration of the hydronium ion at equilibrium will also be X. Okay, now we have filled in the rice table. Part C says to plug in all three of these values in terms of X. So 0.50 minus X, and then X and X. Plug in these values from the bottom row of your rice table into the Ka expression shown below. So here we have the Ka expression for acetic acid. Concentration of the hydronium ion, X. Concentration of the acetate ion, X. And then divided by the concentration of acetic acid, which is 0.50 minus X. Now we have to solve for X. So now what I'm going to do on this next slide is I'm going to show you two different ways to solve for X. The first way involves using the quadratic formula. So our expression looks like the following. We have X times X on the top, and on the bottom we have 0.50 minus X, and then that's our Ka expression, so we set that equal to the value of Ka that we were given in this problem, which is 1.8 times 10 to the negative 5. The next step to solve for X involves multiplying both sides of the equation by 0.50 minus X. Then I will do the appropriate mathematical manipulations to get a quadratic equation. So right now I have X squared plus 1.8 times 10 to the negative 5x minus 9.0 times 10 to the negative 6 equals 0. And when I use a quadratic formula equation or a quadratic formula solver, what I get is the value of X, which represents the concentration of the hydronium ion at equilibrium, is equal to 0.00299 moles per liter. Now you might be thinking at this point, do I need to use the quadratic formula or the quadratic equation in order to solve AP chemistry problems on the AP exam? And the answer is no, absolutely not. On the AP chemistry exam, you will not need to use the quadratic equation to solve any mathematical calculations. So how can we do this particular problem and solve for X in an easier way that avoids using the quadratic equation? Well, it's based on the fact that acetic acid is a weak acid. So as a weak acid, it is only partially ionized in aqueous solution. Now, you can make the following assumption in order to simplify the math in part C. If X, which is the concentration of the hydronium ion at equilibrium, is much smaller than the initial concentration of acetic acid, which was 0.50 molar, then the assumption that we make to simplify the math is that 0.50 molar minus X is approximately equal to 0.50 molar. So the value of X being much smaller than the initial concentration of the acetic acid allows us to make this simplifying assumption. Let's take a look. So now on the bottom, we have X times X on the top, but on the bottom, we just have 0.50. There's no minus X term, and this does make the math so much easier. Take a look. I have X squared divided by 0.50 is equal to the value of Ka for acetic acid, which is 1.8 times 10 to the negative 5. I will multiply both sides of the equation by 0.5. I have X squared equals 9.0 times 10 to the negative 6. There's no quadratic equation at all. All I have to do to solve for X is take the square root of 9.0 times 10 to the negative 6. And when I do that math, I get that X, which is the concentration of the hydronium ion at equilibrium, is 0.0030. Now, compare the answer that I got using the quadratic formula with the answer I got using this simplifying assumption. You can see that those numbers are almost identical, 0.0299 and 0.0030. So that was a reasonable assumption that definitely makes the math easier. So on the AP Chemistry exam, you will not need to use the quadratic equation. So that is the concentration of the hydronium ion at equilibrium in this solution of 0.50 molar acetic acid. Now that we have filled in our rice table in terms of X, and we have solved for X, we can go back to that rice table and replace the X with the actual number. So 0.003, that now is substituted into the rice table. So I'm going to fill in either minus or plus 0.003. I will then do the math from top to bottom. So 0.50 minus 0.003 becomes 0.497. So hopefully you can see why that simplifying assumption was a reasonable one. 0.497 is so close to 0.50 that was a reasonable assumption that the value of X is much smaller than the initial concentration of the weak acid. All right, so I now have numbers in my final row of my rice table. 0.497 is the concentration of acetic acid at equilibrium, and 0.003 is the concentration of both the acetate ion and the hydronium ion. So in part D, it says the following. In part C, you solve for X, which represents the concentration of the hydronium ion at equilibrium in 0.50 molar acetic acid. Calculate the pH of 0.50 molar acetic acid. How do we calculate the pH if we know the concentration of the hydronium ion? We're going to take the negative log of the concentration of the hydronium ion. So the negative log of 0.003 moles per liter, that is equal to a pH of 2.52. Now remember that earlier in part A of this question, we had made a prediction that the pH of 0.50 molar acetic acid was supposed to be higher than the pH of 0.50 molar hydrofluoric acid. So recall that in question 14, we were told that the pH of the 0.50 molar hydrofluoric acid was 1.74, and now we have just determined that the pH of 0.50 molar acetic acid is 2.52. So our prediction did come true in that because acetic acid had a lower Ka value and was a weaker acid, its pH was going to be higher. So that prediction did come true. All right, now moving on to our next question. This is question 16. Question 16 says the following. Hypochlorous acid, HOCl, is a weak acid that forms when chlorine dissolves in water. HOCl molecules react with water molecules to form hypochlorite ions, OCl-, and hydronium ions. Part A. Write the balanced chemical equation for the ionization of HOCl in aqueous solution. Now, in previous questions in this packet, questions 14 and 15, you have already seen a balanced chemical equation for the ionization of a weak acid in aqueous solution. So in question 14, it was the reaction between HF, hydrofluoric acid, and water, and that reaction produced F- and the hydronium ion. In question 15, you saw the balanced equation for the reaction of acetic acid with water to produce acetate and the hydronium ion. Let's use these two equations that we have already seen as a template for how to write the balanced chemical equation for the ionization of HOCl, another weak acid, in aqueous solution. So our reactant will be the weak acid HOCl and water. And when HOCl reacts with water, a proton, H+, is transferred from the weak acid to the water to produce the conjugate base, OCl-, and the hydronium ion. So the answer to part A should look very similar to other reactions that you have seen where a weak acid transfers a proton, H+, to water, producing the conjugate base and the hydronium ion. All right, now let's take a look at part B of this question. Part B says to write the Ka expression for hypochlorous acid. Remember that the Ka expression will be products over reactants. So the Ka will be the concentration of OCl- times the concentration of the hydronium ion, and then divided by the concentration of HOCl. We do not include water because pure liquids and solids are not included in the equilibrium constant expression. So that answer is part B, the Ka expression for hypochlorous acid. Now, let's move on to part C of this question. Part C says the following. The pH of 0.50 molar hypochlorous acid is 3.92. Make a rice table to help you calculate the concentrations of HOCl, the hydronium ion, and the hypochlorite ion, OCl-, at equilibrium in a solution of 0.50 molar hypochlorous acid. This rice table that we're going to make now should look very similar to the rice table that was created in question 15. So the first row of the rice table is the reaction. That would be the reaction between molecules of hypochlorous acid and molecules of water to produce the conjugate base, OCl-, and the hydronium ion. Since we are given the initial concentration of hypochlorous acid is 0.50 molar, that goes into the initial row of the table. Initially, before the reaction takes place, the concentration of the hypochlorite ion is 0. And the concentration of the hydronium ion is very, very small. It's approximately 0. For the change, as the reaction proceeds, the concentration of hypochlorous acid will decrease by some number that we don't know yet, so I'll say minus X. And the concentration of the products, OCl- and the hydronium ion, they're going to increase, so I'll say plus X and plus X. At equilibrium, the concentration of hypochlorous acid will be 0.50 minus X, and the concentration of the hypochlorite ion, OCl-, and the hydronium ion will be X and X. Now, we're not going to solve for X like we did in question 15, and the reason why we're not going to solve for X is that we are already given the pH. So if we're already given the pH is 3.92, then we can calculate the concentration of the hydronium ion directly from the pH value. Remember that if we know the pH, the concentration of the hydronium ion would be 10 raised to the minus pH, in this case, 10 raised to the minus 3.92. So when we do that math, 10 raised to the minus 3.92 on our calculator, we get 1.2 times 10 to the negative 4 moles per liter. We can fill that into the bottom row of our rice table. That means that at equilibrium, the concentration of the hypochlorite ion, OCl-, is also 1.2 times 10 to the negative 4 moles per liter. And technically, 0.50 minus 1.2 times 10 to the negative 4 is 0.4999, so that's so close to 0.50, I'm just going to go ahead and say 0.50 moles per liter. In other words, the concentration of hypochlorous acid at equilibrium is so close to the initial concentration that 0.4999 is just rounded up to 0.50. So look at the final row of the rice table. We have the concentration of all three species, so we can calculate the value of Ka for hypochlorous acid. So remember that earlier in part B of this question, we had already written the Ka expression for hypochlorous acid. The Ka expression is concentration of OCl- times concentration of hydronium divided by concentration of hypochlorous acid. And looking at the final row of this rice table, we now have numbers for all three of those species. We know the concentration of everything in solution at equilibrium. Let's go ahead and plug in the numbers from the final row of the rice table into the Ka expression. So on top, we have 1.2 times 10 to the negative 4 times that same value, 1.2 times 10 to the negative 4. And on the bottom, we have 0.50. So when we do that math and plug in those numbers into our calculator, we get the value for Ka for hypochlorous acid. And that works out to be 2.9 times 10 to the negative 8. So that value is the Ka for hypochlorous acid. Let's move on to the next question in the packet, which is question 17. What I have done on this slide is showing you a table in which each of these acids, hydrofluoric acid, HF, acetic acid, HC2H3O2, and hypochlorous acid, HOCl, have been written for you in this table with the Ka values. So we have 6.8 times 10 to the negative 4, 1.8 times 10 to the negative 5, and the number that we just got for hypochlorous acid, 2.9 times 10 to the negative 8. As you go from left to right across the table, you can see that the Ka values are getting smaller and smaller. So what does that mean in terms of the relative strength of these three acids? Well, it means that HF, which has the highest value for Ka, is the strongest acid, and it means that HOCl, hypochlorous acid, which has the smallest Ka value, is the weakest acid. Question 17. Use the information in the table above to answer the following questions. Part A. When comparing two different acids, the stronger acid is the acid that has the higher Ka value. Now focus on the pH. All three of these acids had a concentration of 0.50 moles per liter. Look at the three pH values. As we go from the strongest acid to the weakest acid from left to right across that table, we see that the pH of the strongest acid was 1.74, and the pH of the weakest acid was 3.92. So part B of question 17, when comparing two different acids that have the same initial concentration, so in this case they were all 0.50, the stronger acid will have the lower pH. So what's nice about this table is you can compare the relative strength of the acid in terms of their Ka values, and if all of these acids have the same initial concentration, you can compare the relative strength of the acids by looking at the pH. Now, before we get to question 18 of this packet, take a moment to process the information that I'm presenting on this slide. There is an interesting relationship between the initial concentration of a weak acid and the percent ionization of the acid. I've got data for two different weak acids, hydrofluoric acid, HF, and acetic acid, HC2H3O2. There's a lot of data on this slide. Let me go ahead and help you process it, and I'll move from left to right across the data table. So in the first column, we see the initial concentration of the acid. I start with a concentration of 1.0 molar, and I go down to a concentration of 0.010 molar. So, as you can see from top to bottom, the initial concentration of the acid is decreasing. Now, let's take a look at the pH. The pH changes from 1.59 to a value of 2.64. So the pH is increasing. This is not a surprising result. That's what you would expect. If you dilute the concentration of the acid, you would expect the pH of the solution to increase. The next column is also not surprising. If you dilute the concentration of the acid, you would expect the concentration of the hydronium ion in solution to decrease. But the last column of the table on the far right, this is the surprising result. Take a look at the percent ionization of the acid. It goes from 2.6% to 23%. So the percent ionization of the acid is actually increasing as we dilute it with water. There's a similar trend for acetic acid. I go from 1 molar to 0.010 molar. So the initial concentration of the acid is going down, and yet the percent ionization is actually going up. So here is question 18. Based on this data, we can say that as the value for the initial concentration of the acid decreases, the value of the concentration of the hydronium ion also decreases. The pH of the solution increases, but here is that surprising result. The percent ionization of the acid actually increases. Now, how can we explain why, when you dilute a weak acid, why does the percent ionization of the acid actually increase? The inverse relationship between the initial concentration of a weak acid and the percent ionization of the acid can be explained in terms of Le Châtelier's principle. During Unit 7, Equilibrium, you learned the following. If an aqueous equilibrium system is diluted with water, the concentrations of all aqueous species are decreased. As a result of this change, the aqueous equilibrium system shifts toward the side of the equation that has the higher number of moles of aqueous particles. In the equation for the ionization of a weak acid in aqueous solution, there's 1 mole of aqueous particles on the left, on the reactant side, and there's 2 moles of aqueous particles on the right, on the product side. Therefore, dilution with water results in a shift toward the side of the equation with a higher number of moles of aqueous particles, which would be from left to right. That's why the percent ionization of an acid will increase upon dilution with water. Another way to see this is to actually do a Q versus K comparison. Now, suppose that you have a weak acid and 500 milliliters of water is added to 500 milliliters of the weak acid solution. As a result of that dilution, each concentration would decrease by a factor of 1/2. So I have a Q versus K comparison where I multiply each concentration in the equilibrium constant expression by 1/2. So you can see 1/2 times the concentration of H plus, 1/2 times the concentration of A minus, and 1/2 times the concentration of the weak acid. But as a result, because there are 2 aqueous species in the numerator and only 1 aqueous species in the denominator, dilution with water causes the value of Q to become less than K. So this causes a shift. When Q is less than K, there is a net conversion from reactants to products, from left to right. So as a result, when Q is less than K, and that shift occurs from left to right, the percent ionization of the acid increases. So again, we can use Le Châtelier's principle to explain why, when you dilute a weak acid, you increase the percent ionization of the acid. Okay, well, hopefully that explanation made sense. Now, you have seen several examples of weak acids. Let's examine the properties of weak bases. On this slide, in the table on the left, are examples of strong bases, group 1 and group 2 hydroxides, such as sodium hydroxide, potassium hydroxide, calcium hydroxide, and strontium hydroxide. Strong bases are 100% dissociated into ions in aqueous solution. On the right side of this table are examples of weak bases, which are only partially ionized in aqueous solution. A few examples of weak bases are ammonia, NH3, methylamine, CH3NH2, pyridine, C5H5N, the fluoride ion, F-, and the acetate ion, C2H3O2-. Now let's take a look at question 19 involving a weak base, ammonia. So ammonia, NH3, is a weak base that ionizes in aqueous solution according to the equation shown below. Part A, write the expression for the equilibrium constant Kb for this reaction. So to write the Kb expression, it's going to be products over reactants. That means it will be the concentration of the ammonium ion, NH4+, times the concentration of the hydroxide ion, divided by the concentration of ammonia, NH3. Remember that we do not include solids and pure liquids in the equilibrium constant expression, so water is not included in the Kb expression. Now, you may recall that earlier in this video, when you wrote the answer to question 14, part A, you wrote the expression for Ka for hydrofluoric acid, HF. And then, when you compared the Ka for hydrofluoric acid with the generic Ka expression on the AP Chemistry equations and constant sheet, that they were very similar to each other. Let's do the same kind of thing. Let's compare the answer to number 19, part A, which is the Kb expression for the weak base ammonia, NH3, with the generic Kb expression for any weak base that we can see on the AP Chemistry equations and constant sheet. So take a look. So as you can see, side by side, we have in the numerator concentration of hydroxide times the concentration of the conjugate acid, and in the denominator, we have the concentration of the weak base. So the generic formula for a weak base is capital letter B, and the generic formula for its conjugate acid is the formula Hb+. So hopefully you can see that those two expressions are very similar to each other. So when a generic weak base, symbolized by capital B, reacts with water, the weak base acts as a proton acceptor, accepting an H+ ion from a water molecule to produce the conjugate acid, Hb+, and the hydroxide ion. Now, let's move on to part B of question 19. In part B, it says the following. The pH of 0.50 molar ammonia, NH3, is 11.48. Calculate the value of the hydroxide ion in 0.50 molar ammonia. Now, if we know the pH, we can calculate the concentration of H+ by doing the reverse of the negative log. So the reverse of the negative log is 10 to the minus pH. So the concentration of H+ is equal to 10 to the minus 11.48. And when we do that calculation, we get 3.3113 times 10 to the negative 12 moles per liter. So that number is the concentration of H+. We're trying to get the concentration of the hydroxide ion, OH-. So remember, on the equation sheet, you can use the Kw expression to solve for the concentration of hydroxide. Because according to the Kw expression, the concentration of H+ times the concentration of OH- equals the Kw, which is 1.0 times 10 to the negative 14. And since we already know the concentration of H plus is 3.3113 times 10 to the negative 12, I'll go ahead and take that value and solve for the concentration of hydroxide by doing 1 times 10 to the negative 14 divided by 3.3113 times 10 to the negative 12. And when I do that math, I get the concentration of hydroxide, which is 0.0030 moles per liter. Now, I will show you another way to get that same answer by doing a slightly different calculation. We know the pH of this solution is 11.48. There is a relationship between pH and pOH, which we looked at earlier in this video. 14 is the sum of pH plus pOH, and since the pH is 11.48, that means that the pOH would be 14 minus 11.48. So 14 minus 11.48 is 2.52. And if the pOH is 2.52, then the concentration of hydroxide would be 10 to the minus 2.52. And if we do 10 to the minus 2.52, we get that same answer. So 0.0030 moles per liter, that is the concentration of hydroxide. So I've shown you two different ways to get that answer to part B. Now let's move on to part C of this question. It says, use the formula below for percent ionization of a weak base, and your answer to part B, which is 0.0030 moles per liter, to calculate the percent ionization of the base in a solution of 0.50 molar ammonia, NH3. Remember that a weak base is only partially ionized in aqueous solution, so we are expecting a rather small number for the percent ionization. Let's take a look. We have a ratio for percent ionization of a weak base, and that is the concentration of hydroxide at equilibrium divided by the initial concentration of the weak base. So using the numbers that we have for part B and part C, that would be 0.0030 moles per liter, the concentration of hydroxide, divided by 0.50, the concentration of ammonia. When we do that math, that ratio times 100, we do get a very small number. We get 0.60%. That indicates that this is a weak base because only a very small percentage of those ammonia molecules are ionized in aqueous solution. Now, here are two important categories of weak bases that are listed in the table below. So these two categories of weak bases include neutral molecules that contain an atom with a lone pair of electrons that can accept H+, as well as anions or negative ions that are the conjugate base of a weak acid. So all of these species can behave as weak bases. Examples of neutral molecules that contain a lone pair of electrons that can accept H+ include ammonia, NH3, methylamine, CH3NH2, hydroxylamine, NH2OH, and pyridine, C5H5N. So all four of these molecules contain a nitrogen atom with a lone pair of electrons that can accept H+, and they behave as weak bases. On the right side of this table, we have negative ions or anions that are the conjugate base of a weak acid. So these examples include acetate, C2H3O2-, hypochlorite, ClO-, nitrite, NO2-, and hydrogen carbonate, HCO3-. So all four of these anions came from a weak acid. So they are the conjugate base of a weak acid, and they behave as weak bases in aqueous solution. Now, before I get to question 20 in the packet, I'd like to talk about the mathematical relationship between Ka and Kb for a conjugate acid-base pair. So in this example, I have acetic acid, HC2H3O2, which is a weak acid, and then I have its conjugate base, which is acetate, C2H3O2-. So these two species represent a conjugate acid-base pair. and the mathematical relationship between the values of Ka and Kb for a conjugate acid-base pair is represented by the two equations below. We have Ka times Kb is equal to the Kw, which is 1 times 10 to the negative 14. We also have another way of representing this relationship using pKa plus pKb, and that is equal to 14, assuming that we are at 25 degrees Celsius. So the example that I'm showing on this slide is for the weak acid, acetic acid, and its conjugate base, acetate. However, you should know that this relationship of Ka times Kb equals Kw, or 10 to the negative 14, this works for any conjugate acid-base pair. So what I'm showing you is acetic acid dissociating into the ions H+ and acetate. And the Ka expression is written on the right of this equation. Now, directly underneath this equation, I'm going to write the reaction for the ionization of the acetate ion as it reacts with water to produce hydroxide and acetic acid. The Kb expression is shown on the right side of this equation. Take a look at what happens when we add these two equations together. The first equation involves acetic acid. The second equation involves acetate. So when I add these two equations together, watch what cancels out on opposite sides of the equation. So I can cross off the weak acid, acetic acid, on the left and on the right. I can cross off the weak base, acetate, on the left and on the right. And so when I add these two equations together, what I get is the autoionization of water, which has the equilibrium constant Kw. So what I'm showing you on this slide is that when you have Ka and Kb, the product of Ka times Kb, which is what you get when you add two equations together, you multiply the equilibrium constants together, Ka times Kb equals Kw. So take a look at the bottom of this slide. If I multiply the Ka for acetic acid times the Kb for acetate, look what crosses off on the top and the bottom. I can cross off the acetate ion. I can cross off the acetic acid molecule, and what I end up with is H+ times OH-, or the Kw. So again, to summarize, when you have a conjugate acid-base pair, Ka times Kb equals the Kw, or 10 to the negative 14. This equation is on the AP Chemistry equations and constants sheet. I just wanted to explain how that equation works. Now, let's take a look at question 20. Question 20 says the following. Propanoic acid, HC3H5O2, ionizes in aqueous solution according to the equation shown below. Part A. Write the expression for the equilibrium constant Ka for this reaction. So the Ka expression for this reaction will be products over reactants. That means we have the concentration of C3H5O2- times the concentration of the hydronium ion, H3O+, divided by the concentration of propanoic acid. Remember that we do not include water as a liquid in the equilibrium constant expression. So this is the expression for Ka for this reaction. Now, let's take a look at part B of this question. Part B says the pKa for propanoic acid is 4.88. Calculate the value of Ka for propanoic acid. Now, when we take a look at the AP Chemistry equation sheet, we can see that the definition of pKa is equal to the negative log of the Ka. But in this problem, we already know that the pKa value is equal to 4.88. What we're trying to calculate is the value of Ka. So what we have to do mathematically is the opposite of taking the negative log of a number. And so the opposite of negative log is 10 to the minus something. So it's going to be 10 to the minus, in this case, 4.88. That will give us the value of Ka. So on my calculator, when I did 10 to the minus 4.88, I got an unrounded answer of 1.3183 times 10 to the negative 5. And according to the rules, for significant figures, when it comes to things like pH or pKa, we only count the digits to the right of the decimal as significant figures. So 4.88 actually has two significant figures. So based on that rule, I'm going to go ahead and round off my Ka to two significant figures. So that Ka value would be 1.3 times 10 to the negative 5. So that is my answer to part B. The Ka for propanoic acid is 1.3 times 10 to the negative 5. Now let's move on to part C of this question. Part C says calculate the pH of 0.50 molar propanoic acid. Now in this video, you've already seen several examples of rice tables for a weak acid. Here is another example of a rice table that you can use to calculate the pH of 0.50 molar propanoic acid. So here is my rice table involving the reaction between propanoic acid and water to produce the propanoate ion, C3H5O2-, and the hydronium ion. And the reason why we're doing a rice table is so we can calculate the concentration of the hydronium ion. Then, once we have that value, we can take the negative log of the hydronium ion to get the pH, and that will be our answer to part C. Let's fill in the initial row of this rice table. So that's the concentration of propanoic acid, 0.50 moles per liter. And then initially, we have a concentration of 0 for this conjugate base, the propanoate ion. And the concentration of the hydronium ion at the beginning of the reaction would be approximately 0 because it's a very, very small number. In pure water, it's 10 to the minus 7, so it's so small, it's practically 0. The change would be minus X for the propanoic acid, and then plus X for the propanoate ion, as well as plus X for the hydronium ion. Again, this pattern looks very similar to the rice tables that you've seen earlier in this video. So at the equilibrium, we have 0.5 minus X, and then we have X and X. Let's plug in these values from the final row of the rice table into the Ka expression. So here is our Ka expression for propanoic acid. On the top, we have X times X, and on the bottom, we have 0.50 minus X. Earlier in this video, remember that there's that simplifying assumption that we make to avoid using the quadratic formula. And that simplifying assumption is that the value of X is so much smaller than the initial concentration of the weak acid that we can assume that 0.5 minus X is equal to 0.5. That's because X is much smaller than 0.5. We do this so that we can simplify the math, and you'll never have to use the quadratic formula to solve a question on the AP Chemistry exam. Now, the next step is to solve for X, so I'm going to multiply both sides by 0.5. I get X squared is equal to 6.5 times 10 to the negative 6. I will take the square root of both sides of the equation to solve for X. I get X is equal to the square root of 6.5 times 10 to the negative 6, and that gives me 2.550 times 10 to the negative 3 moles per liter, which I will round off to approximately 2.6 times 10 to the negative 3 moles per liter. So that is my concentration of the hydronium ion. I'm only one step away from obtaining the pH of this solution. So the negative log of the hydronium ion, the concentration of the hydronium ion gives me the pH. The negative log of the concentration of the hydronium ion gives me negative log of 2.6 times 10 to the negative 3. When I do that math on my calculator, I get the answer to part C, which is 2.59. So the pH of 0.50 molar propanoic acid is 2.59. Now, let's take a look at part D of this question. The propanoate ion or C3H5O2-, ionizes in aqueous solution according to the equation shown below. Part D says calculate the value of Kb for the propanoate ion, C3H5O2-. I'm going to show you two different methods to calculate the value of Kb. You may recall that before I began talking about question 20 of this packet, I showed you the mathematical relationship between Ka and Kb for a conjugate acid-base pair. And that's what we have here. We have a conjugate acid-base pair between propanoic acid and the propanoate ion. Now, what I'd like to do in part D is to show you two different methods for calculating the value of Kb for this weak base, the propanoate ion. So let's go ahead and take a look at the AP Chemistry equation sheet. And as you can see, highlighted on this slide, I'm going to choose the equation that says Kw equals the product of Ka times Kb. So let's start with that equation. And by the way, Kw is equal to 1 times 10 to the negative 14. Okay, so here's the equation. Ka times Kb equals 1 times 10 to the negative 14. Now, earlier in this question, we had already determined the value of Ka for propanoic acid. So in that earlier part of this question, we determined that the value of Ka was 1.3 times 10 to the negative 5. And so if that's the Ka for propanoic acid, what I'm trying to find is the Kb for its conjugate base. So based on this math, all I have to do to calculate Kb is simply rearrange this equation a little bit. So it's going to be that Kb is equal to 1 times 10 to the negative 14, which is the Kw, divided by the Ka for propanoic acid, which is 1.3 times 10 to the negative 5. And so when I do this math on my calculator, I get approximately 7.7 times 10 to the negative 10. So that is the answer to part D. But as I said, I'm going to show you two different methods to get this answer. So now let's go back to the AP Chemistry equation sheet. And this time, I'm going to focus on this equation, which says pKw is equal to the sum of pKa plus pKb. And the pKw is equal to 14. Let's start with this equation. pKa plus pKb is equal to 14. Now, earlier in this question, we were given that the value of pKa for propanoic acid is 4.88. So that was given earlier in this question. All I have to do now is rearrange this equation to solve for pKb, and that would be 14 minus 4.88. And 14 minus 4.88 is equal to 9.12. Now, 9.12 is not the answer to part D, but I'm very close. If the pKb for propanoate ion is equal to 9.12, well then the Kb for the propanoate ion is 10 to the minus 9.12. So the Kb is equal to 10 raised to the minus 9.12 power. And when I do that math on my calculator, I get approximately 7.6 times 10 to the negative 10. So I've shown you two different methods to get the answer to part D, and they were very similar mathematically. I got either 7.7 or in this case 7.6 times 10 to the negative 10. All right, well, hopefully that made sense. And now let's go ahead and move on to part E of this question. In part E of this question, it says, calculate the pH of 0.50 molar sodium propanoate. So the chemical formula for sodium propanoate is Na for sodium, followed by C3H5O2. And as you can see at the top of this slide, it's the propanoate ion, which has the chemical formula C3H5O2-, that behaves as a weak base. So the propanoate ion ionizes an aqueous solution according to this equation shown below. So my strategy for doing the calculations of pH in part E is to first set up a rice table. Now, when I write this rice table, the R, which is the reaction, is going to be the reaction of the propanoate ion with water to produce its conjugate acid, so propanoic acid, as well as the hydroxide ion. And what I'll be doing is calculating the concentration of the hydroxide ion in this solution. Because if I can figure out the concentration of the hydroxide ion, I can definitely determine the pH. Now, if you're wondering, what about the sodium ion? The sodium ion is kind of like a spectator ion. It's not doing anything to affect the pH. So we can focus our attention on this weak base, which is the propanoate ion. So now let's move on to the initial row of this rice table. We are given a solution that has a concentration of 0.50 molar. And again, not worrying about the sodium, the concentration of the propanoate ion in this solution is given as 0.50 molar. But initially, let's assume that this reaction with water has not yet occurred. So on the right side of the equation, I'm going to assume that these two concentrations of the products are 0 and 0 because the reaction has not happened yet. Now you can see that I put sort of approximately 0 for the hydroxide concentration because technically in pure water, the concentration of hydroxide is 10 to the minus 7 moles per liter, but that number is so small, it can be ignored as negligible. All right, what about the change row of this rice table? I'm going to do this in terms of x. And since all of these coefficients are 1, it's going to be minus x for the decrease in the concentration of the propanoate ion. And then for the products that are being formed, it would be plus x and plus x. Now I can just carry these x values down into the final row of this rice table. And so it looks like this from left to right. 0.5 minus x, and x, and x. Well, now that I know the numbers in terms of x in the final row of this rice table, the next thing I'm going to do is write the Kb expression for this weak base, the propanoate ion. So it's going to be products over reactants for that reaction that you can see here on this slide. So products over reactants, the Kb expression is concentration of the propanoic acid times the concentration of hydroxide divided by the concentration of the propanoate ion. And then obviously I'm ignoring water in this Kb expression because water is a pure liquid. Now we have data in the final row of this rice table, so it's going to be x times x in the numerator of this Kb expression, and then 0.5 minus x in the denominator of this Kb expression. And as I've already mentioned earlier in this video, to make our math easier, we can employ this simplifying assumption that x is much smaller than this number, this 0.50. So now our expression is simplified to x squared divided by 0.50. And I'm setting this equal to the Kb, which is 7.6 times 10 to the negative 10. Remember that you are not going to need to use the quadratic equation on the AP Chemistry exam, so that simplifying assumption in the denominator of this Kb expression, it is a valid assumption because x is a very small number compared to 0.5, and of course it makes our math so much easier. Again, our goal is to calculate the concentration of the hydroxide ion, because if we can do that, then we can definitely calculate the pH. All right, let's continue solving this problem. So I have x squared divided by 0.50, and that is equal to the Kb, 7.6 times 10 to the negative 10. I'm going to go ahead and multiply both sides of this equation by 0.5. Now I get x squared is equal to 3.8 times 10 to the negative 10. Here comes my square root. So x is equal to the square root of 3.8 times 10 to the negative 10. And so when I did that math, I got 1.9494 times 10 to the negative 5, and that's my value of x. I'm not going to round off this number very much at this point because I'm not done yet, so I'd rather keep some extra digits of precision until I'm all done. Well, what did I just figure out if x is equal to 1.9494 times 10 to the negative 5 moles per liter? Well, hopefully you can see in the numerator of this Kb expression that x is, in fact, the concentration of the hydroxide ion. So I am only 2 steps away from determining the pH of this 0.50 molar sodium propanoate solution. I'm only 2 steps away. The first step is to get the pOH, and then the final step is to get the pH. So how do I get the pOH? Recall that pOH is equal to the negative log of the concentration of hydroxide, so all I have to do is take the negative log of this number. So the negative log of 1.9494 times 10 to the negative 5 gives me a pOH value of 4.71. Now, 4.71 is not the pH, but I'm only 1 step away from figuring out the pH, because if pH plus pOH is equal to 14, then 14 minus pOH is equal to pH. So 14 minus 4.71 gives me a value of 9.29. Now, that should make sense to you, because since the propanoate ion is a weak base, we would expect the pH of this solution to be greater than 7. So 9.29 is a very reasonable answer for the pH of a weak base solution. Well, hopefully all of those calculations made sense, including how I treated the Rice table and made that simplifying assumption. So this is the answer to part E. It is also the last question in this packet. So we have come to the end of the video. I hope that you found all of these answers and explanations helpful. Thanks for watching.